Hi everyone, welcome to my YouTube channel, and in this video we will talk about 3 more dynamic programming problems. This one will be on house robber problems, and so let's get to these problems. Here, this is our first problem, this is our second problem, and this is our last problem. So I want you guys to pause this video for a second, try to come up with your own solutions for these problems. Alright, so let's look at our first problem. This is problem 198. Here we have a constraint, meaning that we cannot rob two adjacent houses. So that's one constraint. So if you look at this problem, always remember how many states do we have to consider. We need to know we need to know the current position, like which house are we trying to rob or not. So there will be seventh house, second house, etc. So that will correspond to the index of our num. Another one that we have to consider is, do we rob this house or do we not? So that is our second state that we have to consider. So we have two states to consider. Fortunately for us in this problem, because if you look at our second state, we only have a binary choice, right? We either rob or we don't. In this case, we can just have a one for loop instead of two for loops to solve this problem. So that is good thing for us. So what should be our DP? So my definition of DP in this problem is that for DP of I, that means the maximum amount we can rob while satisfying that constraint that we cannot rob two adjacent house. That's our definition. And in terms of mathematical notation, we will have something like this. So DP of I equals maximum. We take the maximum of DP of I minus 1 or DP of I minus 2 plus nums of I. Now, so what does this guy mean? The first guy, DP of I minus 1. That means we do not rob our current house. That's ith house. So that means we don't rob ith house. For the second case, we have to look back at I minus 2 because we cannot rob adjacent house, so I minus 1 is not allowed. And then we have to add nums I. And then we take the maximum of those two numbers. Alright, now, so that's the recurrence relationship. And what about initial condition? Well, so DP of 0, what's the maximum amount we can rob on our first house? There will be just nums of 0. So that's what we have. Lastly, we have DP of 1. Now DP of 1, well, this one makes sense, right? DP of 0. But DP of 1, when I is equal to 1, we have DP of minus 1. We don't have minus 1, so we set that equal to 0. And there will be just nums of 0 and nums of 1. So we take the maximum of nums of 0 and nums of 1. That's for DP of 1. So those two are initial conditions, and let's see our code for this problem. So here on the right hand side, we have the code for this problem, and this code is exactly what you just saw on my iPad as a pseudocode. And let's try to run this. Alright, so that's for this problem, and let's look at the next one. Next one will be this guy. For this problem, it is almost identical to the previous one, except that we have a circular array. So that means we have a 14 here as well. So something like this, right? This guy, something like this. Does that make this problem more difficult? Actually, it's not. So what do we have to consider? If you pick this guy, so let me use this color. If you pick this guy, then you cannot pick them. So if you start with this one, 4, then the maximum you can go is this guy. You cannot go to 14 because this is a circular array. 14 is here, so 4s. So this guy's adjacent house will be this one and 14. Because of that, the maximum you can go from here is this guy. So let me use this one. So starting from here, this is how much we can go. Okay, now we have another case to consider, right? So that would be this one. If we start at this position, say this one, then the maximum we can go is until this guy. This is what we have, and this is how much we can go. And that's pretty much it for this problem. So we apply exactly the same code here, this one, twice. So for this one, and this one. The way I did it is I call this function find maximum, something like that. Then our parameters will be left index and right index and this nums array. We initialize our dp array, so there will be something like this, be 0 times, in this case we would have right minus left plus 1. dp of 0 will be nums of left, and we have we have exactly this one. So we have for loop, so for I in range, so we start from 1 all the way to right minus left plus 1, and we had that if I is equal to 1, that's that's for this guy. So if I is equal to 1, we have dp of I equals max, we take the maximum, and we would have, say, so dp of, it will be dp of I minus 1 and nums of I plus left, and then we have continue. So we have continue, else otherwise we have dp of I is equal to take the maximum, and exactly the same code, I minus 1 dp of I minus 2 plus nums of I plus left, and then we return the last position here. So we return dp of minus 1. Here we would have, basically we would have find max. Left in this case would be this one, there will be 0, and this one will be n minus 2. This one will be find max, there will be 1 and n minus 1, and that's for this code. And so let's see how this works. On the right hand side we have the code for this problem, and let's just take a look at this code. So this one is our edge case. If you look at this one, we can have the length of our nums array can be 1. In that case we just return the number, so we have nums of 0. Otherwise we return like the maximum of these two functions, and this is our function that you just saw on my iPad. And let's run this. Alright, so that's for this problem, and the next one will be this guy. This problem, I have two approaches. The first one is using the memoization, so there will be dynamic programming top-down approach, and the second approach is using DFS, depth first search. So let's look at the first approach. So following the constraint, here we have at each node we can either rob the house or not. If I say, let's say we choose to rob this house, then you cannot rob B and E, but you can rob C, D, E, and F. If you choose not to rob this house A, then you can rob B and E. You cannot rob C, D, F, and G. Alright, so okay, so that's what we have. How do we write a code for this? So we initialize memoization. So this is our dictionary memo. So we check if the node is either empty or not. If it is empty, then we return 0. So in other words, if the node is in our memoization table, then we return this guy. So when we have this recursion, it's gonna be like this. We'll be looking at like going in this direction, and then we comes up and then we go down. So in this phase, we do not have overlapping sub problems. But when we are working on, say, if we are working on this like subtree, then we will have overlapping sub problems from like the left subtree. So that's where this will comes handy. Now we have either two choices, right? We either rob or we do not rob. Let's say we are at dp of A. If we decide to rob this house A, then we have to add this current value. There will be node.bell, and then we also have to look at not this children. So we do not look at these children, but we look at the children beneath there is children. So we have C, D, F, and G. So we have to look 2 levels below itself. So that's why we first have to check if node.left is empty or not. If it is empty, then it is pointless to check like this node. So we return 0. If this is not empty, then we have to run this. So we have to run dp of left. So there will be this guy, B, and then dot left. That will be this guy, right? So there will be, so this will be dp of A dot left, and this one will be dp of a dot left dot right. So you add them. So this is what you have. So you have a addition here. You'll be adding that value to this, and plus we also have to look at this guy, right? This guy. If the node dot right is empty, then we just return 0, right? But if this is not empty node, then we have to look at its children below. So that will be what? So this guy will be dp of a dot right dot left, and this one will be dp dot a dot right dot right. So that's what's going on here. Right dot left, right dot right, and you add them up, and you have 3 additions going on here. 4 addition actually. So that's when you decide to rob at this house A. You also have a choice not to rob house A. In that case, you take these 2 guys, right? So there will be dp of a dot left plus dp of a dot right. So that's this guy, and then we have to take the maximum of those 2. So that's what's going on here. We take the maximum of either rob or we do not rob, and then that will be the value of this memoization table. So memo of node will be equal to whatever maximum value we get from these 2, and then we return that guy. That's for this problem. That's the memoization approach, and let's look at depth first search. Alright, so let's look at the second approach for this problem. Here we will be using DFS. This is my DFS code. So this guy and this guy, that's my DFS code, and our code will look something like this. So we have, so we run DFS of root, blah blah blah, that's this guy, and then we have a answer equal to DFS of root. This one should be null, and then we take the maximum, return maximum of answer. So that's the code for this problem. Actually, there is subtle mistake here, but let's talk about it later. Let's just briefly look at our DFS code. Suppose we have say DFS of B. Now the node itself is not empty, so we skip this part. Left will be DFS of C, and then the right will be DFS of D, right? So you keep going down and down, and at DFS of C, well, it is not empty. You go beneath the level, 1 level beneath C, and we notice that it is empty, so we return 0, 0. So DFS of C, this guy will be this one, and DFS of D will be this one. If you look at this one, we have an array with 2 entries. The first entry means the maximum amount you get by robbing house B. In this case, for the second entry, there will be the maximum amount you get by not robbing house B. You may be tempted to say that, well, in that case, first one will be B, and then the second one will be this guy plus this guy, right? So that's C plus D. That's why you have, if you look at here, node.bell plus, we have a left of 1 plus right of 1. So in this case, left of 1 is 0, right of 1 is 0. So we have B, and then the next one will be left of 0 plus right of 0. There will be C plus D. And you may be tempted that this may be right. In some cases, this may be right, but in some cases, this code is not right. So here is a counter example. So let's look at this guy. If you use this approach, like this code, then this is what you get. So let me just erase a little bit here. So 5, 0, 0, 0. And we go up, we take this one will be node.bell, then we take this guy plus this guy, right? So that's why you get 5. You also have an empty node here, and then here you have a 0, 0, and you can take node.bell, that will be 2 plus 5, this guy, and then this guy, well, 2 plus 5 plus 0, but it is 2 plus 5, and then 3 is from this guy, right? So we have a left of 0, and then right of 0 is 0, so we have 3. You go up, we have 6 plus 3, this guy, and then we have 2 plus 5, this guy. And then we take the maximum and we get 9. But actually, our answer should be what? 13. 11, right? Why is that? You can pick this guy and pick this guy. There is no law that says if you pick this guy, you must pick this guy, and so on. You can actually do this. You can pick this one, skip this, skip this and you can pick this one. So we have 11, but according to this one, we get 9. So how should we modify this? Very simple. Here, we change this part. So instead of getting, left of 0 plus right of 0, we take the maximum of left plus maximum of right. And using that, we get the right correct tree, and we see that the maximum value is 11. In other words, this part, it really corresponds to if we are not picking that current node's value, then we have to look at its children. We have to look at the left children and then the right children. We have to say, we have to get the maximum. So in that case, we have to take the maximum of its left children. We have to get the maximum of its right children. If you do that, you get the right answer. Let's see the code for this problem. So on the right hand side, we have the code for this problem, and the first code, this part, the uncommented one, so this part is the one where we use depth first search, and let's run this. Okay, so that's what we get, and let's run the one where we use top-down memoization approach. Okay. Alright, so that's for this problem, and hope you guys learn something from this video. For me, I personally like the third problem because I couldn't come up with tabulation, so bottoms up approach for this problem, because we have a binary tree. Still memoization works, so top down still works, and I really like this depth first search approach. Dynamic programming, like the memoization approach is really depth first search plus memoization. So you can think of dynamic programming as just depth first search plus memoization. So once you understand that, I think the second approach makes more sense. Like why are we using depth first search? Anyway, that's for this video, and right now is 1 a.m. in my time, and I'm about to fall asleep. So if you think I lose some focus like towards the end, and if that's the case, please write a comment, and I'm more than happy to answer you guys questions in my comment section. Well, hope you guys have a great sleep and I will see you next time. Okay, bye bye.